That is impressive.
You see, I want to see.
Well, you might as well just keep doing it as long as this is messed up.
One more time?
Yes. Is it recording now?
But this not do it with the oxygen and iron.
Yeah, but no.
What?
Huh?
Nothing.
I don't want to touch it now.
It's good. Let's get all ready.
Put all of it in there. No.
You get more burn marks in the ceiling, maybe.
Oxygen tank
We're
on.
lucky.
Okay.
You're gonna do it quick because you know there's a hole over in the side of it. You know?
Early home.
Wasn't too early. See, it's just right. I thought there was some stuff hanging.
Okay. Why did I do this?
Does it look cool?
Because it was cool? Well, yeah, that's part of it. But what's the difference between the iron burning just in the atmosphere, which is 19% oxygen, and the iron burning in there?
More oxygen
Could
reaction,
it be
so
that
the
there was
reaction
more
comes
oxygen
faster.
in enclosed space? So
What?
could it be because there's more oxygen in an enclosed space, or because there's more amounts of oxygen in there?
There's more oxygen in a small space in there, yes.
Because the fact that there's more oxygen makes the reaction happen quicker.
But either way, we're getting iron reacting with oxygen.
To get
Right? It's the same reaction either way. What's the difference? Brian Patrick Henry said we had more oxygen in a small space. That's true. What did you say when you were standing up here?
That the reaction should happen quicker.
you had to change the
Reaction
concentration.
did what?
It happened quicker.
It happened quicker.
It happened,
Yes. That's it.
They release the same energy in a shorter amount of time.
Yes. It released the same energy, but much faster. The same reaction occurred. You get the same product from it. The same amount of reactant would be consumed, at least as far as the iron is concerned. Okay? The only thing that's different between the two is the rate. This section is on kinetics. What does kinetics mean? Motion. So this section is on chemical kinetics, so we're going to be studying the rates of reaction. So what is it exactly that sped up the rate of our reaction?
The change in concentration of the reactant of the product with time.
Did you read that on your notes?
Yes.
Yes, that's it. There was a high concentration of oxygen in this Erlenmeyer flask. So that changed the rate of the reaction, sped it up considerably. I can't believe it burned a hole through my flask.
Can I see?
Did you see that? Burn a hole right through it. Huh? It's a little warm.
Pass it around.
Okay, let's start on our notes. Who's going to be clicking, girl?
Robert. I nominate Robert.
Okay. The point that I have to stress is kinetics is separate from thermodynamics. What do you mean by that? What I mean is kinetics is how fast a reaction proceeds. When we study thermodynamics, which we'll do a few units from now, thermodynamics, we'll look at the change in energy, we'll look at the change in entropy, and we'll figure out if a reaction will occur spontaneously. That is completely independent of kinetics. Whether it's spontaneous or not has nothing to do with how fast the reaction proceeds. Does anyone have a piece of candy? Piece of candy.
It's candy.
You got a piece of candy?
That's how they were
Okay.
James Woods.
There's a piece of candy. You can keep it, but what I'd like you to do is open the wrapper and then just set it on your desk. We're gonna observe it.
We just did that.
Okay, you got it open? It's candy, no matter what it is mostly sugar. And sugars break down. There's monosaccharides, disaccharides. There's probably a disaccharide, sucrose, fructose. But it breaks apart into glucose, and glucose is C6H12O6. And it reacts with oxygen to produce carbon dioxide and water. That reaction is called glycolysis. And it is, the thermodynamics of that reaction is it's spontaneous. The universe favors this reaction in the forward direction. So, free person, is it reacting with oxygen? Do you see, you won't see the carbon dioxide, I doubt you see the bubbles, but is there a little puddle of water around your candy now?
Wait, so is it?
You don't see any water around it? Nothing. But it's spontaneous.
It's still happening, it's not quick.
It's not happening quick enough, you have to change the rate.
Thermodynamically favorable
So,
as written in the forward direction, so what are you doing wrong?
does that mean if we take that piece of candy and
You
put
don't have
that
to go to
in
wrap it, you can eat it. What?
Does that mean if we put that piece of candy in there with oxygen and leave it on your like lab paper for a while, and eventually just turn it into water?
Yeah.
Let's do it.
Well, and there's other stuff in there. There'd be some, red dye number 2 looks like, and probably some filler,
Oh,
sort of starch binder.
And they'll have to do a lot of it.
You did?
Like, there's that one big piece, and then there's a lot of little piece specs that do the exact same stuff. They're gonna just suck in the sun.
In science club, when we do the thermite, we're gonna have molten iron, so it'll probably.
Termite?
Thermite!
Termite.
Me and Jan learn how to make thermite from there.
Is that reaction occurring yet? This reaction occurs in your body, in every cell of your body. Glycolysis is occurring in your cells right now. This is where you derive energy in your cells, glycolysis. The reverse of it, you know what the reverse reaction is? If I flip that around, where does that occur? In plants. Photosynthesis. Reverse reaction. And the reverse reaction is not thermodynamically favorable. It's not spontaneous. It requires an input of energy. Where do the plants get that energy?
From the sun.
My son.
Les sun, you speak French.
Yes.
Yeah, they get the energy from the sun. So the energy, the input of energy drives a non-spontaneous reaction. Okay? Is it any water yet? You see anything there? Are you looking closely?
I think we should.
Okay, so what's the point? It's thermodynamically favorable, but thermodynamics is separate from kinetics. We could be waiting a long time for that candy to turn into carbon dioxide and water. So in your cells, what are you doing to speed up this reaction?
Breathe.
Eat the meat.
Huh?
You breathe.
No.
You breathe.
What?
Are you breathing? You breathe.
That is your energy.
Are you
This is
breathing?
where your cells derive energy, from glucose.
Do you
You
breathe?
get energy, you get that whole ATP cycle going. That's where you get energy, from glycolysis. Now, what are you doing in your cells? If you're doing it, you don't even know what you're doing.
Breathing. I'm pretty sure it's breathing. Is it breathing?
No.
Respiration.
What speeds up a reaction?
Energy.
Catalyst.
Enzymes.
Oh.
Catalysts. In your body, you have enzymes that act as a catalyst. You're both right. Don't be, oh. An enzyme lowers the activation energy, starts the reaction occurring, and it goes spontaneous.
Let's put the piece of candy in oxygen.
Click.
Let's see if that will cook it. Well, we're gonna make that for a while.
All right. Reaction rate is a change of concentration of a reactant or a product with time. Make sure we don't go with 15 minutes. When you get 14 something, stop it. And our rate will typically be molarity change in molarity for a second. So if we have reaction A to B, click. Real simple. The formula for calculating rate will be the negative
There's something.
change in concentration of A divided by change in time. Where have you been?
Press.
Excuse me?
Oh.
You're interrupting my class.
I feel myself.
Well, that's just a little bit.
Okay. Can anybody tell me why there's a negative in front of that formula?
What is the A stand for right now?
Okay, we have a reaction A going to B.
Yes.
So we can measure the rate of this reaction by the change in concentration, the brackets is concentration, right?
Yes.
Change in concentration of A over change in time.
Because A decreases with time.
It's negative because A is a reactant. As the reaction occurs, A goes bye-bye.
Okay.
Click again. Yes, so it's negative. Click again. Which would be equal to the rate of change in concentration of B over change in time. Note that B doesn't have, when we use a product, we don't have the negative in front of it. Why don't we have the negative in front of it when we're looking at the rate of formation of B?
It's your product.
It's what you're forming. As the reaction proceeds, its concentration goes up. Questions?
Right, so does that
Naki?
mean, I have a question. So does that mean if it's like, if it's a reaction that goes in both ways and it has a reverse reaction and also occurs spontaneously, that it reaches equilibrium, that the concentration of A will also be positive, or that value could also be positive and equal to the other values?
At the point you reach equilibrium, your rate will be zero.
Okay,
The concentration is no longer changing.
okay. Now I get it.
Well, no, that's not true. The concentration of your reactants and products will not be changing. There's no change. So the rate of the forward reaction will be equal to the rate of the reverse reaction. Yes. Any water there yet? Keep an eye on it. Click. All right, because your reactant decreases with time, A is negative. Click again. Come on, clicky girl. Click again. If we were to graph it at the point where time equals 0, we're all reactants. We have no products. And then it goes down. Concentration of the reactant goes down at the same rate as the concentration of the product goes up because they're 1 to 1. The coefficients were 1 to 1. So the rate of disappearance of A is the same as the rate of appearance of B. Note that it's not a straight line. Because it's a curve, what can we deduce from this line?
So the rate is.
That the rate is, you're off to a fine start.
The rate is increasing.
No. I don't see any, on our graph, I don't see anywhere where the rate is constant. It's a curve all the way down, but you're right, it's probably going to level out here, isn't it? But as long, and when it does, the reaction stops. But while the reaction is occurring, it's a curve. So the rate is not steady, is it?
No.
Where's the rate the fastest? Well, you got that wrong. Where's the rate the fastest?
The rate is fastest at the beginning of the reaction.
The rate is the fastest at the beginning.
Why is that?
Okay?
But it has more of a reaction.
You know, I've told you the qualitative analysis in this class is just as important, if not more important, than the quantitative analysis.
Yes, it's fast.
So we're going to be doing some calculations, and that's important. But whenever you're asking yourself why, or I'm asking you why,